Every so often, the universe tosses us a surprise guest, a cosmic hitchhiker that drifts in uninvited, ignores all the orbital rules, and then disappears before we even remember to offer snacks. In 2024, one such wanderer quietly slipped into the neighborhood. Astronomers gave it a formal name, 3IATLAS, the third officially confirmed interstellar object to ever visit the solar system. But informal names like the Space Tourist, the Galactic Drifter, or Rock with Trust Issues might fit just as well. The 3I stands for Third Interstellar, while ATLAS comes from the Asteroid Terrestrial-impact Last Alert System, a pair of wide-field telescopes perched atop Hawaiian volcanoes. ATLAS's day job is scanning the heavens for objects that might one day crash into Earth. Think of it as the universe's Neighborhood Watch program. Instead of a planet killer, though, it spotted something far more poetic, a tiny body hurtling through space on a trajectory that screamed, "I don't live here." The system designed to warn us of doom had, ironically, discovered a cosmic tourist instead. At first, 3IATLAS looked like any other dim blip of light. Astronomers measure such things not in pixels but in patience. You stare long enough at a sky full of static, and sometimes the static moves. But when the orbital data rolled in, jaws dropped. The object's speed was extraordinary, over 26 kilometers per second relative to the Sun, a velocity so high that even the Sun's massive gravity couldn't reel it back. Every planet, comet, and asteroid in our system eventually circles the Sun. This one was just passing through. If our solar system were a busy airport, 3IATLAS was the flight that burst through the runway, waved at the control tower, and kept going. Its path followed a hyperbola, not the graceful ellipse of regular orbits. A hyperbolic orbit means one thing: this traveler came from interstellar space and would soon leave it again. No return ticket, no baggage claim. It wasn't the first of its kind. Back in 2018, we met ʻOumuamua, a strangely elongated, tumbling object that behaved like a comet but looked more like a space French fry. 2 years later came 2I Borisov, a classically icy comet that made astronomers feel slightly more comfortable about their physics again. Then arrived 3IATLAS, less flashy, less photogenic, but no less significant. It proved that interstellar visitors aren't rare flukes. They're just hard to catch in the act. The moment scientists realized what they were looking at, the race was on. Observatories across the world swung their telescopes to follow this tiny wanderer before it faded back into darkness. Observing an interstellar object is like trying to read a license plate on a car that's speeding past at 40,000 miles per hour while you're standing in a hurricane. Every photon counts. Each image is a piece of a cosmic puzzle, millions of years in the making. But what makes 3IATLAS so special is not just its trajectory, it's what its presence represents. This object wasn't born around our Sun. It formed in another stellar nursery somewhere in the Milky Way, perhaps orbiting a young star that was still throwing planets together like a celestial potluck. During those chaotic early days, giant planets can fling debris outward with gravitational slingshots, sending rocks and ice balls into eternal exile. 3IATLAS was one of those exiles, a cosmic refugee crossing the interstellar wilderness for millions, perhaps billions, of years before stumbling into our solar night. Just imagine that journey. No light, no heat, just the occasional brush with starlight from distant suns. For ages, 3IATLAS traveled through the galactic dark like a message in a bottle. Then, by chance and gravity, it wandered close enough to the sun for our tiny species on a blue planet to notice it. If the universe had a sense of humor, this was it. An alien rock dropping by right after humanity built enough telescopes to see it. Of course, the cosmic guest didn't come bearing gifts or threats. It simply moved on, oblivious to the scientific fanfare. But for astronomers, it was like finding a fragment of another civilization's history. Not the aliens themselves, but a piece of their front yard. Its composition could hold clues about the dust and gas cloud that formed its home star. Every atom in it is a souvenir from a different corner of the galaxy. And then there's the sheer perspective it gives us. Our solar system often feels like the entire stage, but objects like 3IATLAS remind us we're just one set in a galactic theater of hundreds of billions of stars. Matter doesn't stay put. Stars share it, trade it, throw it away. In time, even some of Earth's own dust will escape into the void, becoming someone else's mystery visitor. Humor helps digest that existential idea. Picture Earth as a homeowner who just saw something fly through the yard. Did anyone see where that came from? Meanwhile, 3IATLAS is already halfway to the door, mumbling, "Sorry, wrong solar system." If rocks had passports, this one would be stamped in a dozen languages of starlight. Even its timing adds to the cosmic drama. It arrived just as astronomers were developing faster survey telescopes, AI-based sky scanners, and planetary defense programs. In a way, 3IATLAS was a gift, a test subject for our new cosmic eyes. And it proved something comforting, too. Interstellar space isn't empty. It's alive with motion, exchange, and stories. Before long, 3IATLAS will be gone, heading back toward the cold expanse between the stars. It will fade from our telescopes, but not from our scientific memory. It joined a short list of visitors that have expanded our definition of home. To study it is to peek beyond the solar system without ever leaving it, to touch another world's past just for a moment. So yes, 3IATLAS was tiny, dim, and easily overlooked. But its story is immense. It reminds us that the universe isn't a collection of isolated islands. It's a web of motion and chance encounters. And every so often, a small visitor from another star drives through our cosmic neighborhood, flashes its alien license plate, and keeps on cruising through the infinite night. It all started, as many great discoveries do, with a tiny flicker of light that almost no one noticed. One faint speck on a digital sky map, buried among thousands of others. But that's the beauty of astronomy. Every frame of data might contain something extraordinary, hiding in plain sight. In early April 2024, one of the twin ATLAS telescopes atop Mauna Loa in Hawaii picked up an object moving just a bit differently from the rest. ATLAS, short for Asteroid Terrestrial-impact Last Alert System, was built to spot near-Earth objects that might someday collide with our planet. Think of it as the cosmic version of check engine lights for the sky. It scans the heavens several times a night, snapping rapid-fire exposures of the same region to catch any dots of light that shift position. Now, Most moving dots are routine, harmless asteroids circling the sun like obedient citizens. But every now and then, one breaks the pattern. In this case, astronomers reviewing the ATLAS data noticed a faint object that didn't behave as expected. Its motion didn't match any known asteroid catalogs, and its apparent brightness didn't fit the standard curve for an object that close. It was subtle, but suspicious, like a car drifting across multiple lanes for no reason. Atlas's algorithms automatically flagged it for follow-up, but even advanced software has its limits. That's when the human eyes stepped in, those patient scientists who spend their nights sorting through sky maps, drinking too much coffee, and hoping for cosmic surprises. As they examined the images frame by frame, they saw that this faint visitor's path was steeper, faster, and far less curved than normal. At first, the team thought they might be looking at a long-period comet, the kind that loops in from the outer Oort cloud once every few million years. But something didn't add up. When they ran orbital simulations, the calculated eccentricity, the measure of how stretched an orbit is, came out greater than 1. That's like finding a circle so wide it never closes. In orbital mechanics, eccentricity 1 means hyperbolic trajectory, the cosmic equivalent of a one-way ticket. And that's when the aha moment struck. This object wasn't coming from the solar system. It was coming through it. To double-check, astronomers at observatories across the world joined the chase. The Pan-STARRS system, the Lowell Observatory, and even amateur astronomers with high-end backyard telescopes contributed new data points. Each measurement helped refine the orbit, trimming away uncertainty. Within days, the evidence was overwhelming. The object was inbound from interstellar space. You could almost hear the collective gasp echoing through the astrophysics community. Only 2 such visitors had ever been confirmed before, and both had shocked the world. Now, against all odds, a third had arrived. For context, that's like winning the cosmic lottery 3 times in 1 decade. The galaxy had been tossing pebbles our way for eons, but we'd only just developed the eyes to see them. So what exactly does the process of identifying such an alien rock look like? It's part science, part detective work, and part sleepless obsession. First, astronomers gather astrometric data, precise measurements of the object's position in the sky over time. Each night adds a few more dots to a cosmic connect-the-dots puzzle. Then comes the math. Using orbital determination software, programs with unromantic names like Find Orb, they feed in those coordinates to calculate the best fit orbit. The goal: to determine whether the sun's gravity can hold the object in a bound path. If the numbers say yes, it's a local. If they say no, congratulations, you've just discovered an interstellar intruder. Of course, the universe loves false alarms. Sometimes observational errors can make a local object look interstellar. To rule that out, teams perform what's known as orbit fitting and Monte Carlo simulations, essentially rerunning the data thousands of times with tiny variations to see if the hyperbolic signature holds. For 3IATLAS, it did. No matter how they adjusted the data, the trajectory remained stubbornly unbound. Once confirmed, the International Astronomical Union, IAU, designated it 3IATLAS, the 3I marking its place as the third known interstellar object. And, just like that, a faint dot became headline news. But the real detective work had only begun. The discovery triggered an urgent campaign of observations across the electromagnetic spectrum, from visible light to infrared. Every telescope that could track it was booked. Time on these observatories is precious. Entire research proposals compete for a few hours of viewing. Yet, for an interstellar visitor, astronomers will bend every rule. The challenge: this object was faint, very faint. By the time it was detected, it was already racing away from the sun, fading fast. Observing it was like trying to photograph a fly zipping past a flashlight in the dark. The ATLAS survey had spotted it just early enough to give scientists a small window of opportunity. Days, not weeks, to extract data before it disappeared for good. While this was unfolding, data scientists were running complex models, comparing its trajectory with known galactic motions. Where had it come from? Could its direction be traced to a specific star system? Sadly, with the data available, pinpointing its origin was like tracing a single raindrop back to the cloud it fell from. Still, the path hinted that 3IATLAS entered our solar system from the direction of the constellation Lynx, suggesting a long interstellar voyage through the galactic disk. Astronomers couldn't help but marvel at the odds. The Milky Way contains roughly 100 billion stars, each surrounded by debris fields of rock and ice. Statistically, many of those fragments must be ejected into space during planetary formation. Some drift forever. A few cross paths with other stars, and once in a while, one happens to pass close enough to be spotted by a civilization that finally has the tools to see it. That civilization, of course, being us, the universe's overly curious primates, armed with glass lenses and equations. The discovery also underscored how far our technology has come. 2 decades ago, ATLAS didn't exist. Even the best sky surveys lacked the coverage and automation to catch something so transient. Now, with automated scanning, AI-driven anomaly detection, and near real-time coordination among global observatories, humanity can spot interstellar rocks on the fly. Literally. And the humor? Well, it wrote itself. When the first orbital calculations were posted online, one astronomer quipped, "This rock didn't do its homework on Kepler's laws." Another replied, "Yeah, it's not even enrolled in this solar system." In the end, what began as a faint blip turned into a revelation, a story of teamwork, math, and cosmic curiosity. The universe didn't send 3IATLAS with fanfare. It whispered it into a data stream, trusting that someone, somewhere, would notice. And we did. That's the beauty of science. Sometimes it's less about shouting discoveries and more about listening carefully to the quiet signals the universe leaves behind. The universe has rules, laws of motion, gravity, and celestial etiquette. Most cosmic travelers follow them politely, circling the sun in neat, predictable ellipses like well-behaved commuters on a galactic highway. But every now and then, a rebel comes barreling through, ignoring all the speed limits, cutting across traffic and blasting past the sun without even signaling. That rebel was 3IATLAS. When astronomers first plotted its orbit, they realized it wasn't following the calm, egg-shaped path of an ordinary asteroid or comet. Instead, it was on a hyperbolic trajectory, a shape that doesn't loop back. To put it simply, a hyperbola is the universe's way of saying, this one's just passing through. If an ellipse is a racetrack, a hyperbola is a drive-by. To understand how unusual that is, let's step back to the basics. Every object moving under gravity, from moons to spacecraft, follows one of four possible orbital shapes: circle, ellipse, parabola, or hyperbola. Circles and ellipses mean the object is bound to the central mass, trapped in a gravitational relationship. A parabola sits right on the edge, the escape velocity threshold. And a hyperbola? That's an escape in progress. The Sun, despite being unimaginably massive, has its limits. Its gravitational pull fades with distance, and if an object is moving fast enough, it can't be captured. That's where 3IATLAS comes in. A cosmic rock zooming through the solar system at nearly 26 kilometers per second relative to the Sun. For context, that's fast enough to travel from New York to Tokyo in under 8 minutes. It's also well above the escape velocity of the solar system at the distance it was observed. In other words, even the Sun's gravitational grip, strong enough to hold entire planets, couldn't keep this visitor from leaving. You could almost imagine the Sun shaking its fiery fist, shouting, "Hey, you can't just zoom through here!" And 3IATLAS replying, "Watch me." Most comets and asteroids don't have that kind of attitude. They're loyal to the Sun, bound by gravity's invisible leash. Their orbits are elliptical, meaning they swing close to the Sun at one end, perihelion, and then drift far away before looping back again, aphelion. Halley's comet, for example, returns every 76 years, like a cosmic regular on a predictable schedule. Even distant bodies in the Oort cloud, icy leftovers orbiting billions of kilometers away, are still gravitationally tied to the Sun. But 3IATLAS? It doesn't belong to that club. Its orbital eccentricity, the number that defines how stretched an orbit is, measured greater than 1, a clear mathematical signature of a hyperbola. That means it didn't start its journey here, and it definitely wasn't staying. Instead, it was flying along a curved, open-ended path, using the Sun's gravity not as a leash, but as a slingshot. Here's where things get beautifully weird. When an object on a hyperbolic path enters the solar system, it accelerates as it approaches the Sun, whipping around it at incredible speed, then slows as it exits, but never enough to be caught. It's the same principle NASA uses for interplanetary missions, except instead of a spacecraft designed for it, this was a random rock from another star. Imagine 3IATLAS as a tourist driving through the galaxy who spotted our solar system's exit ramp, thought, "Cool view," did a U-turn around the Sun, and kept going. No souvenirs, no postcards. What makes this kind of orbit so fascinating is that it carries a story written in velocity. In space, speed is history. The faster something moves, the deeper it's past. If an object travels faster than the escape velocity of a solar system, that means it was kicked out, possibly by a massive planet, a stellar collision, or a gravitational chain reaction billions of years ago. Hyperbolic travelers like 3IATLAS are evidence of the chaos that reigns in young star systems. They're the cosmic debris of violent beginnings, tossed out like interstellar confetti, and they're rare. Even though space is full of rocks, the chances of one crossing paths with us are tiny. Think of it this way. The galaxy is about 100,000 light-years across. Our solar system, in comparison, is a microscopic bubble. The odds of a random interstellar rock entering it are roughly equivalent to tossing a grain of sand across the Pacific Ocean and having it land in your coffee mug. Yet, somehow, it happens. Now, how do astronomers know all this just from numbers on a screen? The answer lies in orbital mechanics, the cosmic detective toolkit. By measuring 3IATLAS's position at multiple times and calculating its changing velocity, they could determine the shape of its path. A plot of its motion against time produced a hyperbolic curve that didn't close, meaning it wasn't orbiting the sun. Even more revealing was the velocity vector, the direction and speed of its motion far from the sun's influence. After accounting for gravitational acceleration near the sun, astronomers could estimate its incoming speed, known as the hyperbolic excess velocity. That's basically how fast it was moving before it even entered our solar system. And that number proved it was interstellar. It wasn't just escaping us, it was already free before it arrived. And the numbers are stunning. To give some perspective, Earth orbits the Sun at about 30 km, the fastest human-made object. The Parker Solar Probe reaches about 190 kilometers at its closest approach. But even at those speeds, Parker remains bound to the Sun. 3IATLAS, with its hyperbolic excess of around 6 kilometers after accounting for the Sun's influence, was moving so confidently that no star, planet, or gravity well could ever fully claim it. It's as if the universe handed it a cosmic get-out-of-orbit-free card. There's something poetic about that. In a galaxy full of orbits, of endless repetitions and cycles, 3IATLAS represents motion without return. It's a symbol of freedom, or perhaps of exile, forever passing from one star's influence to another's, never staying long enough to belong. And while astronomers deal in math and motion, it's hard not to anthropomorphize it just a little. You can imagine the sun's gravitational pull reaching out like a cosmic hand, only for 3IATLAS to slip away with a smirk, muttering, "Not today." This is why the discovery of a hyperbolic trajectory is so thrilling. It's not just about the numbers. It's about what those numbers mean. They tell us that our solar system isn't isolated, that it's part of a larger gravitational conversation. Somewhere out there, another star once had this same rock orbiting it, until a cosmic game of billiards sent it flying into the void. Now, it's visited us, briefly lighting up our telescopes, before continuing its endless journey. 3IATLAS didn't orbit the sun. It swerved around it, fast, dramatic, unapologetic, like a cosmic tourist who just realized it was in the wrong solar system and floored the accelerator. When you hear the word comet, you probably picture something flashy. A sparkling tail streaking through the night sky, a cosmic firework announcing its arrival. But when 3IATLAS came along, astronomers squinted at the data and collectively went, "Wait, what is this thing?" Because 3IATLAS wasn't exactly acting like a comet, but it didn't quite behave like an asteroid either. It was the celestial equivalent of someone showing up at a costume party without clarifying who they were dressed as. That's the mystery at the heart of this chapter. What exactly was 3IATLAS made of? Was it rock, ice, metal, dust? A cursed interstellar fruitcake that's been passed around for eons? The short answer is, we're still not entirely sure. The long answer, the one scientists have been unraveling, is far more fascinating. Let's start with what astronomers could observe. The ATLAS telescopes and follow-up observatories measured how 3IATLAS reflected sunlight. Its brightness and the way it faded over time told us about its surface composition. It appeared relatively faint, meaning it wasn't highly reflective, likely darker than most icy comets, but not as dark as carbon-rich asteroids. That alone put it somewhere in between, suggesting a dusty, mixed surface rather than pure rock or ice. Now, here's where comparisons come in. Humanity has only met two other interstellar visitors before this, one ʻOumuamua and 2I Borisov, and both turned out to be polar opposites. ʻOumuamua, discovered in 2017, was the enigmatic loner of the trio, an object so weird that astronomers still argue about it in conference coffee breaks. It was oddly shaped, possibly cigar-like or pancake-flat, tumbled unpredictably, and accelerated slightly as it moved away from the sun, as if it were venting gas, but with no visible tail. Some scientists suggested it was covered in organic rich material. Others proposed exotic ices like hydrogen or nitrogen, and a few even floated the idea of, you guessed it, alien technology. ʻOumuamua's PR team really didn't have to work hard that year. Then came Borisov in 2019, which behaved much more predictably. It looked and acted like a classic comet, streaming gas, emitting cyanide and water vapor, basically showing off all the hallmarks of an icy traveler. It was, in essence, a normal comet, except for the small detail that it came from another star system. Borisov was the interstellar equivalent of that exchange student who immediately fits in. Now, enter 3IATLAS, quieter, fainter, and far more ambiguous. It didn't display the spectacular tail of Borisov, but it also wasn't the clean, dry mystery that was ʻOumuamua. Instead, it seemed to fall somewhere in between, the cosmic middle child, torn between being a dusty comet or a rocky asteroid. Astronomers analyzed its spectral data. Basically, the light signature it reflected across different wavelengths. The results suggested a neutral to slightly reddish hue, hinting at organic compounds or carbon-rich dust on its surface. That's not unusual. Many outer solar system bodies share that coloration, but in an interstellar object, it's a clue to its birthplace. A reddish tint often means exposure to cosmic radiation over millions of years. High-energy particles in deep space can alter surface materials, breaking molecules apart and forming complex carbon chains called tholins. Dark, tar-like substances that give many distant objects, like Pluto, their reddish-brown tone. So, if 3IATLAS wore a reddish coat, that could mean it spent eons drifting through interstellar space, its surface weathered by cosmic rays until it resembled a well-traveled relic rather than a fresh comet. But things got even stranger when astronomers noticed that its brightness curve fluctuated, slightly but noticeably. That implied it wasn't spherical, it was irregular, possibly elongated. Maybe a fragment, maybe a shard from a larger body. Some even speculated it could be a piece of a disrupted comet or planetesimal, debris flung into space during the violent formation of a distant star system. If true, then 3IATLAS isn't just a random visitor. It's a literal fragment of another world's history, a sample of alien geology, drifting for untold ages, now briefly illuminated by our sun before vanishing back into the dark. And yet, the story deepens. A few observatories detected what looked like a faint coma, a thin haze of gas or dust surrounding the object. That suggested that maybe, just maybe, it was venting a small amount of volatile material, like frozen gases sublimating when heated by sunlight. But the activity was weak, far less than Borisov's dramatic outgassing, meaning that if 3IATLAS did contain ice, it was either buried beneath an insulating crust or largely depleted after its long interstellar journey. Imagine that, a once icy wanderer turned desiccated and scarred by cosmic exposure. If Borisov was the fresh snowball from another star, 3IATLAS was the weathered fossil, ancient, quiet, still carrying the chemistry of its origin, but too exhausted to shine. This leads us to one of the most intriguing scientific questions. Where did it form? The composition clues, a mix of dust and faint volatiles, suggest it originated in the outer regions of a foreign solar system, where ices and dust coexist. Maybe it formed near the frost line of its parent star, that invisible boundary where temperatures are low enough for water and carbon dioxide to freeze. Or maybe it began life as part of a protoplanet, later shattered by a gravitational encounter or planetary collision. Whatever the case, it eventually got yeeted, that's the technical term, out of its home system, condemned to drift endlessly through the galactic void. And that's where it remained for possibly millions or even billions of years, frozen, irradiated, and slowly losing its more volatile materials. By the time it reached us, it was more fossil than comet, a relic more than a traveler. Of course, the lack of direct samples makes all of this educated guesswork. Astronomers have only photons to work with, each one carrying a whisper of information. It's like trying to identify a cake recipe by watching crumbs fall from a passing delivery truck. Hence the humor in this chapter's analogy. Astronomers really are like parents inspecting the mystery lunchbox their kid brought home from space. Is this rock supposed to smell like formaldehyde? Is it safe to lick? Should we refrigerate it? But jokes aside, this kind of mystery is what makes interstellar research so thrilling. 3IATLAS might not be flashy, but it's scientifically priceless, a messenger of chemistry from another world. It shows us that the building blocks of planets, ice, rock, metal, organics, are not unique to our solar system. The same processes that shaped Earth likely occurred billions of miles away around another sun. And, while we may never hold a fragment of 3IATLAS in our hands, its light has already told us enough to know one thing. The ingredients for making worlds are universal. We all come from the same cosmic kitchen. Some recipes just got baked in different ovens. So yes, 3IATLAS might forever keep its secrets locked beneath layers of interstellar dust. But one truth shines through the mystery. No matter where it came from, it's made of the same stuff that makes us: stardust, frozen memories, and a touch of chaos. If space had traffic laws, the Milky Way would be a chaos zone. Hundreds of billions of stars, each with their own entourage of planets, asteroids, and comets, all spinning and flinging debris like a cosmic pinball machine. Amid this chaos, some unlucky rocks are booted from their home systems, forced to drift endlessly through interstellar space. One such runaway was 3IATLAS, the galactic hitchhiker on what we might call the interstellar highway. Now, highway might sound poetic, but in truth, interstellar space is not a paved road. It's an unthinkably vast ocean of near-nothingness. Yet, objects do travel between stars, and it's not by magic or warp drive. It's all thanks to gravity, the invisible puppet master of the universe. Let's start with the big picture. When a planetary system forms, it's a messy process. Picture a young star surrounded by a spinning disk of gas, dust, and rocks. Within that disk, baby planets, called planetesimals, start bumping into each other, merging or scattering like over-caffeinated marbles. Most settle into stable orbits, but not all are so lucky. When a small body strays too close to a massive planet, say, a gas giant the size of Jupiter, things can get chaotic bad. Here's where gravity takes the wheel. A close encounter with a giant planet can turn into a gravitational slingshot, a physics trick both elegant and brutal. The small object swings around the planet, gaining speed by stealing a bit of its orbital momentum. The planet barely notices the loss, but the smaller body, it rockets away like it's been launched from a galactic catapult. If it's moving fast enough, it doesn't just leave that planet's orbit, it escapes the entire solar system. This is likely how 3IATLAS began its journey. Billions of years ago, it might have been an innocent chunk of rock and ice orbiting a star not unlike our Sun. Maybe it circled quietly for eons, part of a belt of comets on the system's outskirts. Then, one day, a gravitational encounter changed everything. Perhaps a giant exoplanet, the size of Jupiter or even Neptune, wandered too close. A quick game of cosmic billiards ensued, and 3IATLAS was the cue ball that got sent flying off the table. It's a scenario that plays out all over the galaxy. Astronomers call it planetary ejection, and it's more common than you might think. Simulations of early solar system formation show that giant planets are like unruly toddlers in a sandbox, constantly throwing smaller toys out. Even our own system did this. Jupiter, in its youth, likely tossed countless comets and icy fragments into interstellar space, sending them sailing away at escape velocities. Somewhere out there, a few of those exiled objects might still be drifting through the galaxy, unclaimed, unloved, but still technically ours. And 3IATLAS? Somewhere in a distant star system, it was probably the same story. A gravitational encounter gave it the ultimate eviction notice. Now, let's talk numbers, because physics doesn't lie. To escape a star system like ours, an object needs to exceed the escape velocity at its location. The speed required to break free from the star's gravitational pull forever. Near Earth's orbit, that's about 42 kilometers per second relative to the Sun. But further out, in the icy regions where comets form, it's much lower, maybe a few kilometers per second. A strong gravitational kick from a massive planet can easily supply that speed. Once ejected, there's no turning back. The object becomes a rogue, traveling freely through interstellar space. It doesn't orbit a star anymore. It orbits the galactic center, joining the great tide of debris drifting between worlds. That's what we call an interstellar object, not bound to any system, moving independently across the galaxy like a cosmic wanderer. But here's the beautiful irony. While ejection sounds like exile, it's also a form of connection. These objects are the messengers of the galaxy, carrying physical samples of the distant systems. Every one of them, including 3IATLAS, holds chemical fingerprints of its birthplace. If we could somehow scoop it up and study it closely, we'd learn about the star that once lit its sky, the planets that shared its space, and the forces that set it adrift. Of course, interstellar space is no gentle journey. Imagine drifting through a near-perfect vacuum for millions of years, with only starlight and cosmic radiation for company. Over time, the surface of such an object becomes scarred, darkened, and dehydrated. The ice sublimates, molecules fracture, and a layer of complex carbon residue builds up. It's like interstellar sunburn, permanent and ancient. By the time 3IATLAS reached us, it had been through the galactic ringer, aged, altered, and possibly stripped of much of its original identity. Still, it survived. Proof that even small, fragile bodies can endure cosmic exile. And in a way, that's what makes its journey poetic. Somewhere, perhaps hundreds of light years away, a star once twinkled over its frozen surface. Then, through a violent twist of fate, it was thrown into the dark, destined to drift forever between suns. Millions of years later, it just happened to pass by ours, briefly catching our attention before continuing on. And yes, if you're wondering, scientists have actually modeled these kinds of trajectories. Using simulations of exoplanetary systems, researchers have shown that for every star like the Sun, trillions of small objects might have been ejected over its lifetime. That means interstellar space is teeming with wanderers. A thin but endless population of comets, asteroids, and icy relics sailing quietly through the void. We just don't see them because they're so faint. Atlas was lucky, and so were we, that it passed close enough for our telescopes to catch the glint of reflected sunlight. It's humbling to realize how interconnected this makes the galaxy. Every planetary system, from red dwarfs to giant stars, has likely contributed material to this invisible highway. Interstellar space isn't empty at all. It's full of lost travelers. The Milky Way is constantly recycling its matter, trading pieces of its worlds like cosmic souvenirs. And that brings us back to the humor of it all. If we anthropomorphized the event, you could imagine some exoplanet sneezing. Achoo! And there goes 3IATLAS, flying off into eternity like an interstellar tissue. Billions of years later, it drifts into another solar system, startling a species of astronomers who point their telescopes at it and say, "What in the Milky Way is that?" So yes, the interstellar highway is real, not a road of asphalt and signs, but of trajectories and probabilities, written by the mathematics of gravity. And 3IATLAS, the tiny traveler from beyond, is just one of the countless commuters on that silent galactic road, forever in motion, forever between homes. If there's one thing the cosmos has perfected, it's the art of nothingness. Between the stars stretches an ocean of near empty space, vast, silent, and indifferent. This is the interstellar medium, the great cosmic wilderness that separates one solar system from another. And somewhere out there, for millions, maybe even billions of years, a small traveler named 3IATLAS was making the loneliest road trip in the galaxy. No snacks, no GPS, no pit stops. Just pure existential drifting. But don't let the phrase empty space fool you. The interstellar medium isn't truly empty. It's just extremely sparse. Imagine a volume the size of your living room containing only a single atom. That's the kind of solitude 3IATLAS lived in. Yet even that vacuum has its texture. There's cosmic dust, fine particles of carbon and silicate drifting like smoke, and a thin fog of hydrogen and helium gas spread across light years. Occasionally, there are cosmic rays, high-energy particles from distant supernovae that zip through space like invisible bullets. This environment is both majestic and merciless. It's so cold that most materials freeze solid, so dark that even starlight fades into a faint whisper. Temperatures can drop to just a few degrees above absolute zero, about 270 degrees. In these conditions, 3IATLAS wasn't flying so much as coasting, conserving whatever motion it had been given when it was ejected from its home system. In the interstellar void, there's nothing to slow it down. No air resistance, no drag, no friction. Once you start moving, you keep going indefinitely. That's the thing about space travel on a galactic scale. There's no speed limit, but also no pit stop. 3IATLAS may have been adrift for tens or hundreds of millions of years, silently crossing the void between stars. To put that in perspective, when this journey began, Earth might have still been a swampy paradise full of early mammals or even dinosaurs. It's like a cosmic time capsule that left before humans existed and only arrived once we'd invented telescopes to notice it. During that endless voyage, 3IATLAS would have encountered the subtle but persistent forces of interstellar space. First, radiation erosion, constant bombardment by cosmic rays and ultraviolet light from nearby stars. Over time, those particles chip away at the surface, breaking molecular bonds, vaporizing lighter elements, and leaving behind a dark, carbon-rich crust. This process, known as space weathering, transforms once bright icy bodies into the dull, reddish-brown objects we observe today. It's essentially the universe's way of giving every traveler a tan, except it takes a few million years and doesn't involve sunlight or sunscreen. Second, there's micrometeorite bombardment, collisions with tiny dust grains moving at tens of kilometers per second. Each impact is minuscule, but over millions of years, they add up. It's death by a trillion paper cuts. The result? The object's surface becomes pitted, melted, and compacted, forming a hardened crust. Think of it as natural armor, a protective shell that seals whatever ices or minerals remain beneath. And then there's the galactic radiation field, a slow, steady drizzle of energy that seeps into everything. Even though it's weak, Over such immense timescales, it can rearrange molecules, producing complex organic compounds called tholins, those reddish coatings seen on many outer solar system objects. So, while 3IATLAS drifted in the dark, its outer layers were chemically evolving, slowly cooking under cosmic radiation until they took on that characteristic interstellar hue. But here's the kicker. Despite how hostile this environment sounds, it's incredibly stable. No collisions with planets, no solar flares, no gravitational chaos. Just silence and motion. In a weird way, interstellar space might be the safest place for a small rock to exist. The Atlas may have survived intact precisely because it was nowhere near anything for so long. It's the cosmic equivalent of staying out of trouble by avoiding civilization altogether. That said, not all of the galaxy is equally peaceful. Every so often, 3IATLAS would have crossed a spiral arm of the Milky Way, regions richer in gas, dust, and star formation. Passing through these could expose it to stronger radiation, denser gas clouds, or even the shock waves from ancient supernova explosions. These encounters would be rare and fleeting, like driving through a storm every few 100 million years. But they would leave subtle marks, perhaps traces of ionized elements embedded in its surface or minute changes in rotation caused by uneven heating. So, how long exactly did this cosmic road trip take? We can't know for certain, but we can estimate. By studying its trajectory as it entered our solar system, astronomers can project its path backward, tracing the direction it came from through the constellation links. But even that only gives a vague region of origin. Space is vast, and the tiniest uncertainty in its velocity translates into light years of ambiguity. The truth is, we might never know which star flung it our way. What we can infer is that the journey was incredibly long. Even if 3IATLAS traveled at tens of kilometers per second, that's only a microscopic fraction of light speed. At that rate, crossing the distance between neighboring stars, say 4 light years, would take around 70,000 years. Multiply that by hundreds of possible light years, and we're easily talking tens of millions of years of uninterrupted travel. 3. Atlas is essentially the ultimate endurance traveler, the space version of a tortoise that just kept going, and going, and going. And because humor helps keep the void less terrifying, imagine 3IATLAS somewhere out there rolling its non-existent eyes saying, "I've been on this road trip for 50 million years, and there's still no bathroom, no Wi-Fi, and no decent radio stations." But there's a strange beauty in that solitude. In the interstellar wilderness, time loses its meaning. There's no sunrise, no sunset, only the faint glow of distant galaxies. The only constant is motion. That's what 3IATLAS embodies. Persistence. Long after its parent star forgot it, long after it lost its icy luster, it kept going. It didn't need purpose or destination, just inertia. When it finally stumbled upon our sun's gravity, it was purely by chance. Out of the countless empty light years, it happened to pass through one small region occupied by a tiny yellow star. And around that star, a planet full of curious beings just advanced enough to notice. We caught it mid-journey, like spotting a lone traveler crossing a desert horizon. And now, as it continues onward, leaving our solar system behind, we're left with the humbling realization that the galaxy is full of such wanderers, timeless drifters tracing invisible paths through the void. 3IATLAS didn't just survive the galactic wilderness, it became part of it, a silent monument to motion, patience, and the enduring will of physics. Long before 3IATLAS became a headline, before its brief fame as an interstellar traveler, it was just another anonymous speck entering the outer reaches of the solar system, a realm so distant that sunlight there is little more than a faint whisper. This is the solar outskirts, a frozen frontier where the sun's warmth fades into darkness, and where the planet's gravitational influence begins to give way to the vast, unclaimed gulf of interstellar space. It was here, on the edge of this frontier, that 3IATLAS first crossed paths with humanity's instruments, a moment that would ignite a global race against time. When astronomers talk about catching an interstellar object, they don't mean physically. They mean photons. Every observation is a battle against fading light. The farther an object is, the fainter it appears, and 3IATLAS was already well into the dim outer solar system when it was first detected. At that distance, even bright comets look like smudges, and this one, small, dark, and fast, was barely clinging to visibility. When ATLAS, the Asteroid Terrestrial-impact Last Alert System, first flagged the object in 2024, it was located somewhere beyond the orbit of Jupiter, roughly 500 million kilometers away. It wasn't glowing with a comet's tail, nor was it moving slowly like an asteroid. Instead, it was racing along a steep inbound path, approaching from the direction of the constellation Lynx, carrying with it the momentum of a million-year journey. The first few days after its discovery were crucial. Astronomers scrambled to gather as much data as possible, a cosmic version of, "Quick, point the telescopes before it ghosts us." And that wasn't just a joke. In celestial mechanics, timing is everything, because interstellar objects move fast, tens of kilometers per second. Their brightness window is painfully short. A delay of even a week could mean the difference between capturing its path with precision or losing track entirely as it fades into the cosmic crowd. To lock down its trajectory, observatories around the world began follow-up observations, each one recording the object's position relative to background stars. These points of light, mere pixels on a CCD sensor, became the breadcrumbs for reconstructing 3IATLAS's orbit. Using software that models gravitational influences from the sun and planets, astronomers refined the numbers until the pattern became unmistakable, a hyperbolic curve slicing through the solar system like a stone skipping across a pond. That orbit told an incredible story. 3IATLAS wasn't looping back around. Its closest approach, or perihelion, would occur inside the inner solar system, after which it would speed away forever. Its inbound speed, angle of entry, and escape velocity all screamed one thing: this object is not from here. But getting a clean orbital solution wasn't simple. The problem with faint, fast objects is that small errors in measurement balloon into huge uncertainties over distance. A positional error of just 1 arc-second, the apparent width of a coin seen from 4 kilometers away, can translate into thousands of kilometers of uncertainty in real space. To fix that, astronomers coordinated globally, timing observations to fill in the gaps as Earth rotated. Telescopes in Hawaii, Chile, Europe, and even small amateur setups contributed measurement. Every additional data point tightened the curve, refining the orbit until its interstellar nature was beyond doubt. And the more the orbit stabilized, the more urgent the work became. Unlike comets that return every few decades, interstellar visitors like 3IATLAS give scientists only one shot. After it departs, it's gone forever. No second chances. No maybe next orbit. You could say it's like trying to study a rare bird that lands once in your lifetime. Lets you take 2 blurry photos, then flies off into another continent. That's why astronomers obsess over early detection. The sooner they spot an object, the longer the observation window before it fades from view. In the case of 3IATLAS, that window was only a few months. Its faint magnitude, around +18 to +19 at discovery, meant it was invisible to the naked eye, requiring powerful telescopes and long exposure times to capture. As it approached perihelion, it briefly brightened, but by the time most large observatories had scheduled it into their programs, it was already receding, slipping away toward the cold edge of the solar system once more. This frantic pace gave rise to one of astronomy's modern challenges: data prioritization. With hundreds of transient events competing for telescope time, supernovae, asteroid flybys, exoplanet transits, scientists must decide which targets deserve immediate attention. Interstellar visitors like 3IATLAS automatically jump to the top of the list. They are, after all, alien material passing through our backyard. But even as data poured in, new mysteries emerged. Some observations hinted at a faint, diffuse glow, possibly a thin coma or dust halo, suggesting mild outgassing. That sparked debates about whether 3IATLAS was a rocky body shedding ancient frost or a comet whose ices had long evaporated. Without more detailed imaging, those questions would remain unanswered. The object was simply too distant, too faint, and too fast. The phrase, "blink and you'll miss it," has never felt more literal. Over a span of weeks, 3IATLAS crossed from one side of the solar system's inner domain to the other, its path bending slightly under the sun's gravity before swinging outward again. By the time Earth's telescopes repositioned to catch its outbound leg, it was already dimming beyond detection limits. Still, the data collected during those frantic months were invaluable. They gave us not just orbital parameters, but a rare snapshot in time. A record of an interstellar traveler's visit to our neighborhood. With those measurements, scientists could simulate its past trajectory and predict its future path, ensuring that even as it fades from view, its journey remains traceable in our records. And perhaps the most poignant part of this story is how quietly it all happened. No blazing streak across the night sky, no visible sign to human eyes, just a faint speck in a digital image, noticed by a handful of watchful astronomers and immortalized in data before it vanished forever. That's the paradox of cosmic exploration. We live in a galaxy full of wonders, yet most of them pass unnoticed, too faint or fleeting for our eyes. 3IATLAS reminded us that discovery often begins in urgency, a race against time, distance, and the slow fade of light. So, when astronomers shouted, "Quick, point the telescopes before it ghosts us," they weren't exaggerating. They were speaking from experience, because in the vast theater of the cosmos, even a brief appearance from a traveler like 3IATLAS deserves a standing ovation. Before the curtain of interstellar night closes again, when astronomers study an object that's billions of kilometers away, there's one brutal truth. They can't touch it, can't chip off a sample, can't smell or taste or weigh it. All they have is light. Every photon that reaches a telescope is a message, one that's traveled through unimaginable distances to whisper something about what it bounced off. And when 3IATLAS came streaking through the solar system, that faint trickle of light became the only clue to decipher what this interstellar visitor was made of. You could say spectroscopy is the universe's version of forensic science. Instead of DNA or fingerprints, scientists look at spectral fingerprints, unique combinations of light wavelengths that correspond to specific elements or molecules. When sunlight hits an object like 3IATLAS, some wavelengths are absorbed by the material on its surface, while others are reflected or emitted. By splitting that light through a spectrograph, a prism-like instrument that separates light into its component colors, astronomers can analyze which wavelengths are missing, dimmed, or enhanced. Each atom, after all, sings its own tune in light. Hydrogen hums in deep red. Sodium glows in yellow. Carbon whispers across the infrared. When scientists decode that symphony, they can reconstruct what the object is made of, even from across the void. For 3IATLAS, this was no easy task. The object was faint, distant, and fast-moving. Capturing its light required some of the world's largest telescopes, including the Very Large Telescope, VLT, in Chile and the Keck Observatory in Hawaii. These instruments are powerful enough to gather photons from across interstellar space and split them into rainbows of data. But even then, the signal was barely above the noise. It was like trying to hear a whisper at a rock concert. Still, that faint whisper told a story. The first analyses revealed a neutral to slightly reddish spectral slope, meaning the reflected light leaned toward the red end of the spectrum. This wasn't bright red like Mars or fresh ice. It was subtle, like dusty brick. That coloration is a hallmark of surfaces that have been exposed to cosmic radiation for eons. Energetic particles bombard the surface, breaking apart molecular bonds and creating complex carbon-based residues known as tholins. Tholins don't occur naturally on Earth. They're unique products of deep space chemistry. Their presence hinted that 3IATLAS had been adrift for millions of years, its surface slowly altered by the harsh interstellar environment. But astronomers wanted to go deeper. If 3IATLAS emitted or reflected any spectral absorption lines, those could reveal the specific materials involved. Perhaps ices like water, methane, or carbon monoxide, or silicate minerals typical of rocky bodies. Each molecule leaves a distinct signature, like a barcode written in light. The challenge? The object's faintness meant that detailed spectroscopy was nearly impossible. The signal-to-noise ratio was so low that even the world's best instruments could only infer general characteristics. Still, certain trends emerged. Its spectrum lacked the strong water ice features seen in typical comets, but it wasn't featureless either. That suggested a mixed composition, possibly a dusty, organic rich crust overlaying dormant ices. To the untrained eye, that might sound inconclusive, but to planetary scientists, it's gold. It places 3IATLAS somewhere between the extremes of ʻOumuamua, dry, reflective, mysterious, and Borisov, wet, gassy, active. In other words, it may represent the median of interstellar material, the quiet, middle ground debris that doesn't flare dramatically but carries deep information about how other planetary systems evolve. And that's where spectroscopy becomes cosmic archaeology. By comparing its spectral fingerprint to known classes of solar system bodies, asteroids, Kuiper Belt objects, Trojans, and comets, researchers can infer where it likely formed. For example, an object rich in volatile ices likely came from the outer, colder regions of its original system. A rockier one would have formed closer to its parent star. 3IATLAS's data suggested a transition object, possibly born near the frost line of its home system, the boundary where temperatures drop low enough for water and carbon dioxide to freeze. Now, because we can't directly observe its interior, astronomers rely on albedo, reflectivity, and spectral slope to infer composition indirectly. A dark surface means it's absorbing more light, likely coated in carbonaceous material. A bright one would indicate fresh ice or silicate rock. 3IATLAS was somewhere in the middle. Dim, but not pitch black, hinting at an aged, radiation-hardened shell covering materials once volatile. To extract this data, scientists had to coordinate observations from multiple observatories across different wavelengths: visible, infrared, and sometimes ultraviolet. Each wavelength range provides different insights. Visible light reveals surface color and overall reflectivity. Infrared detects thermal emission and specific chemical bonds. Ultraviolet can uncover traces of volatile gases or photochemical effects. Combining these data sets is like assembling a jigsaw puzzle from scattered clues. One observatory might catch a hint of carbon absorption. Another might detect a weak reflection curve consistent with silicates. Piece by piece, a rough portrait forms. But perhaps the most fascinating part of spectroscopy isn't what it confirms. It's what it suggests. Because light analysis allows scientists to reverse engineer the story of matter. By identifying certain isotopic ratios, like deuterium to hydrogen or oxygen-17 to oxygen-18, astronomers can distinguish whether a body formed in a warm or cold region of its native star system. Those ratios act as chemical fossils, encoding the temperature and density conditions of its birthplace. Now, we didn't get that level of precision for 3IATLAS. It was simply too faint. But the principle stands. Every photon carries ancient data. Somewhere within its light may lie the record of another star's nursery, frozen in chemistry. And of course, scientists kept their sense of humor intact throughout the process. As one researcher joked, space detectives don't dust for fingerprints. They light scan for magnesium and carbon. It's funny because it's true. Instead of magnifying glasses, they use million-dollar telescopes. Instead of fingerprints, they chase atomic emission lines across the spectrum. The truth is that spectroscopy turns the night sky into a readable book. Every star, planet, and passing rock writes its biography in color. You just need the right instruments and patience to read it. For 3IATLAS, its biography is brief but profound. A reddish, dusty traveler, likely once icy, long hardened by radiation, still carrying the chemical whispers of a foreign sun. Even with limited data, spectroscopy managed to peel back the darkness and show us what this wanderer was made of. And that's the magic of modern astronomy. You can't reach out and touch the object, but with enough light, you can still know it. You can stand on a small blue planet, aim a telescope at the abyss, and from a few stray photons, reconstruct the story of a rock that began its journey around another star long before Earth even existed. Not bad for a bit of detective work, especially when your magnifying glass is made of starlight. Every interstellar object carries a mystery in its atoms, a whisper from the star system that forged it. Though 3IATLAS has long since left its birthplace behind, its composition, motion, and endurance give us clues about the kind of cosmic family it once belonged to. Like a geological fossil or an ancient artifact, it's a remnant from another world's early chaos, a story of creation, collision, and exile, written in the language of physics. So, what sort of place could have birthed an object like this? To answer that, we have to step into the world of exoplanetary archaeology, the study of how other star systems form, evolve, and throw things away. Most planetary systems begin as swirling disks of gas and dust around young stars. Protoplanetary disks, massive, glowing, and volatile. Within these disks, gravity begins to sculpt order from chaos. Dust clumps together. Pebbles become boulders, and boulders become planetesimals, the seeds of planets. It's a messy, violent process. There's no gentle planet formation. It's more like cosmic demolition derby with gravity as referee. In those early stages, countless small bodies get tossed around like shrapnel. Some crash into planets. Some spiral into the star. And some, a lucky few, get flung outward entirely, ejected from their home systems by gravitational chaos. That's how interstellar travelers like 3IATLAS are born. As byproducts of creation, the leftovers of planetary construction. If 3IATLAS originated in such a system, it was probably formed near the outer regions of its protoplanetary disk, where temperatures were low enough for ices to condense. That's consistent with its suspected dusty, icy composition. There, it may have orbited peacefully for millions of years until a planetary giant disrupted the calm. Perhaps a massive gas planet tugging at smaller bodies like a cosmic troublemaker. Imagine a young Jupiter in another system yanking at a surrounding debris with its gravitational might. One unlucky object, 3IATLAS, wanders too close. The planet slingshots it with a gravitational kick strong enough to overcome the star's pull. In an instant, it's gone, flung into the eternal dark, a casualty of celestial adolescence. Some scientists suspect that interstellar objects like 3IATLAS might not just come from single stars like our Sun. They could also originate from binary star systems, where two stars orbit each other. Binary systems are surprisingly common in the galaxy, making up nearly half of all stellar pairs. Now, Binary systems are gravitationally complex. They're like cosmic dance floors where one wrong move sends you flying into the void. If 3IATLAS was born in such a system, its ejection might have been inevitable. Imagine two suns tugging on a disk of comets, constantly reshaping orbits with their competing pulls. Over time, these chaotic interactions can toss countless small bodies into interstellar space. The evidence for this comes from computer simulations. Models show that binary systems are especially efficient at ejecting debris, sometimes 10 to 100 times more so than single star systems. The gravitational tug-of-war between the two stars acts as a slingshot mechanism, launching icy bodies into galactic orbits. If that's the case, 3IATLAS may not have been the only exile. It could be one of trillions of such fragments cast adrift from binary systems all over the galaxy. Its neutral, reddish spectrum adds a bit of weight to this theory. Objects formed around cooler stars, such as red dwarfs or binary pairs, tend to have surfaces rich in carbon compounds that darken over time. It's speculation, yes, but the data we have fits. A body forged in a cold, radiation-exposed environment that's been wandering ever since. If 3IATLAS is indeed a refugee from another solar system, it gives us something precious, a sample of another star's leftovers. To understand its significance, consider what we've already learned from exoplanetary systems observed by telescopes like Kepler, TESS, and ALMA. Many young star systems show evidence of vast debris disks, rings of rock and ice that are basically construction zones for planets. Within them, collisions are constant. Asteroids grind each other to dust, comets vaporize near their suns, and fragments go flying into deep space. These debris fields are the galactic equivalent of construction sites with no safety regulations. Now multiply that by hundreds of billions of stars, and you realize that interstellar space must be filled with wandering objects like 3IATLAS, the discarded building blocks of worlds that never quite made it. Each one carries the chemical fingerprint of its home system, ratios of oxygen, carbon, magnesium, and silicon that vary depending on the local stellar environment. When we analyze those ratios, we get a taste of alien geology. A higher carbon content might suggest formation around a cooler, carbon-rich star. More silicates might point to a hotter, inner disk origin. Even the isotopic composition of hydrogen could reveal whether the body came from a star richer or poorer in heavy elements than the Sun. That's why 3IATLAS, despite its faintness, is a treasure. It's physical proof that planetary formation is universal, that the processes shaping our solar system happen across the galaxy, following the same rules of chemistry and gravity. Of course, the romantic in every astronomer can't help but anthropomorphize a little. Somewhere, billions of years ago, a star once lit the sky over 3IATLAS's frozen surface. It may have orbited peacefully, perhaps alongside sister comets and planetesimals, basking in that foreign light. And then, through a gravitational accident, a planetary nudge, a binary instability, or maybe even a close stellar encounter, it was cast out. If stars could feel attachment, perhaps that one hesitated for a moment as the tiny rock escaped its pull. But physics doesn't do sentiment. The laws of motion care nothing for nostalgia. once 3IATLAS crossed the escape threshold, it was free forever. Maybe it left home because its parent star wouldn't stop talking about its fusion rate. I get it, Dad. You turn hydrogen into helium. We're so proud. Jokes aside, that humorous thought underscores a beautiful truth. 3IATLAS is a messenger from another sun. A piece of tangible evidence that stars across the galaxy share the same cosmic story. They form, build worlds, and cast fragments into the void. Some of those fragments, through improbable luck, find their way to us. Studying 3IATLAS isn't just about understanding one rock. It's about glimpsing the architecture of the galaxy. Every interstellar visitor expands our understanding of how systems form and interact. It tells us that planetary construction isn't a rare miracle. It's a routine byproduct of stellar life. Somewhere out there, near a dim red sun or a chaotic binary pair, another piece of debris may even now be leaving its home system, beginning a voyage that will take millions of years, perhaps to pass near another civilization curious enough to wonder where it came from. So, when we look at 3IATLAS, we're not just studying a visitor. We're reading the story of another world's beginning, one that echoes our own. When 3IATLAS came swooping through the solar system, it wasn't just a visitor, it was a reminder. A reminder that our little corner of space isn't isolated or unique, but part of a much larger family. A galactic web of stars, planets, and drifting matter, all built from the same universal ingredients. You could think of it as a cosmic family reunion, except this one spans 100,000 light years, and nobody remembers who brought the potato salad. Studying interstellar objects like 3IATLAS isn't just about identifying what they're made of or where they came from. It's about context. Understanding how our solar system fits into the broader story of the Milky Way. Every visiting rock, every interstellar particle, is a data point in the grand experiment of cosmic evolution. It tells us not only what other systems are like, but also what we might have once looked like to someone else. Let's start with the basics. All stars, planets, comets, and life forms are forged from the same raw material, stardust. When massive stars reach the end of their lives and explode as supernovae, they scatter heavy elements like carbon, oxygen, iron, and silicon into space. These elements then mix with hydrogen and helium, forming new clouds that give birth to the next generation of stars and planets. It's a continuous cycle of cosmic recycling, a galactic version of composting on a scale so large that even the most eco-conscious human can only dream of keeping up. Our sun, and everything around it, Earth, the moon, your morning coffee, came from one of these recycled clouds about 4.6 billion years ago. And that means other systems like ours, forming across the galaxy, are built from the same stuff. So, when a fragment like 3IATLAS arrives from another star, it's like a genetic relative showing up with matching DNA. By studying it, we learn how much of our own family chemistry is universal, and how much is local flavor. To understand that connection, scientists look for chemical and isotopic signatures, the cosmic equivalent of family traits. For example, the ratio of deuterium to hydrogen, DH ratio, in comets tells us about the temperature and density of the environment where they formed. If we could measure the same ratio in interstellar visitors, we could compare it to comets from our own solar system. If they match, it would mean stars across the galaxy form planets and comets under remarkably similar conditions. If they differ, it would hint that each stellar neighborhood has its own recipe. And that brings us to the punchline. Cosmic chemistry really is the ultimate universal recipe. Everyone in the galaxy uses the same basic ingredients: hydrogen, oxygen, carbon, nitrogen. But the cooking methods vary. Some systems bake their planets hotter, closer to the star, producing rocky worlds like Mercury or Earth. Others chill theirs in the outer zones, creating icy giants and comets. The proportions change, the seasoning differs, but the pantry's the same. When 3IATLAS entered our solar system, it carried a sample of that shared galactic pantry. Even though we couldn't scoop it up directly, its light spectrum provided clues about its makeup: organic dust, silicate minerals, perhaps faint traces of ices long eroded by radiation. These are the same materials that built our comets, asteroids, and planets. It's as if the galaxy were running a franchise model for planet making, and every solar system got a slightly different version of the menu. But the story goes deeper. By comparing interstellar objects with our own, we can trace the exchange of matter between stars, the galactic circulation of raw materials. Over billions of years, stars eject debris that drifts through the interstellar medium, eventually merging into other star-forming clouds. In other words, some of the atoms that make up our solar system, and even our bodies, may once have belonged to another star's planets. This isn't poetic speculation. It's measurable physics. Interstellar dust grains have been detected inside our solar system, their isotopic compositions distinct from local material. Meteorites on Earth even contain pre-solar grains, tiny crystals older than the Sun itself. They're tangible proof that material from distant stars regularly mixes into new planetary systems. 3IATLAS is just a larger, visible-scale example of that cosmic exchange. So, when astronomers analyze interstellar visitors, they're really doing galactic anthropology. They're comparing the cultural artifacts of other systems to our own, looking for shared patterns, unique quirks, and evolutionary pathways. Each discovery rewrites a tiny piece of our cosmic family tree. It also reframes a profound question. How common is life? If 3IATLAS shares the same chemistry as our comets, rich in carbon, oxygen, and complex organics, that suggests the ingredients for life are universal. The same processes that seeded Earth with prebiotic molecules could be happening on millions of other worlds. And that turns the idea of life in the universe from a long shot into something almost inevitable. Humor helps digest this enormity. You can almost imagine the universe as a galactic cooking show. Today, on Milky Way Kitchen, we'll be preparing a solar system. Step 1. Mix hydrogen and helium. Step 2. Sprinkle some silicates. Step 3. Bake under stellar radiation for a few billion years. Serves 8 planets and 1 existential crisis. Beyond the humor, though, lies the realization that studying objects like 3IATLAS turns abstract theory into something tangible. It bridges the gap between our system and the rest of the galaxy, proof that we're not a cosmic anomaly, but part of a recurring pattern. The Sun isn't special for having planets, it's normal. The Earth isn't special for being built from stardust. It's standard-issue galactic matter. Even interstellar visitors aren't rare exceptions. They're just the travelers we've finally learned to see. This is what makes the cosmic family reunion idea so powerful. Every interstellar rock, every comet, every grain of dust drifting between stars is part of a single, vast lineage. We are all offspring of the same molecular ancestors, born from ancient supernovae that seeded the galaxy with the elements of existence. So when 3IATLAS passed through our solar system, it wasn't just a random stranger from another star. It was a distant relative stopping by, waving hello before continuing on its endless journey. And in that brief encounter, it reminded us of something deeply comforting. The universe is vast, yes, but it's also shared. We're not isolated islands in space. We're nodes in a cosmic network, connected by drifting atoms, shared chemistry, and the timeless rhythm of creation and motion. Because in the end, the galaxy isn't a collection of separate systems. It's one enormous family, all following the same stardust cookbook, just experimenting with slightly different recipes. When 3IATLAS drifted into our solar system, it wasn't just an interstellar tourist, it was a living laboratory, a survivor of the galaxy's most brutal environment. For millions of years it had endured a journey through the vacuum between stars, unshielded and alone. No atmosphere to protect it, no magnetosphere to deflect radiation, no convenient spaceship hull to keep it cozy. Just a small, stubborn fragment of matter that said, "Sure, I'll take the long way." For scientists, that makes 3IATLAS an invaluable case study. Because while we've sent probes to the edges of our solar system, no human-made object has ever truly experienced interstellar space for long durations. Even the Voyager spacecraft, the most distant human artifacts, are only a few light hours beyond the Sun's influence. They have just stepped onto the porch of the galaxy. But 3IATLAS, it's been out there, fully immersed in the cold, radiation-soaked wilderness between stars for eons. So, what can we learn from a rock that's essentially the Chuck Norris of cosmic endurance? A lot, actually, about how matter survives in deep space, how radiation reshapes molecules, and how we might design future spacecraft to endure the same conditions. Interstellar space is not the peaceful, silent void Hollywood likes to show. It's more like a slow-motion sandblaster powered by cosmic death rays. It's filled with cosmic rays, which are high-energy protons, electrons, and atomic nuclei, accelerated by supernova explosions and black hole jets. These particles travel at nearly the speed of light, colliding with anything in their path. When they hit the surface of an object like 3IATLAS, they shatter molecules, eject atoms, and alter chemical bonds. Over millions of years, this radiation carves a new identity into the object's outer layers. A dark, carbonized crust called a radiation mantle. It's a slow but relentless process. One cosmic ray might hit a square centimeter of rock every few seconds, and over a few million years, the damage accumulates. The result is a shell only millimeters thick, but chemically transformed, rich in carbon chains, complex organics, and tholins, those reddish compounds that tint many outer solar system bodies. Beneath that, the original ices and minerals remain sealed away, preserved from further erosion. For 3IATLAS, this weathering tells us something profound. Even in the emptiest regions of space, chemistry never sleeps. Radiation doesn't just destroy, it creates. By breaking apart simple molecules, it allows them to recombine into more complex ones, organic compounds that might be precursors to life. If cosmic rays can do that on an inert rock drifting through interstellar space, imagine what they could do on dust grains inside dense molecular clouds where stars and planets form. The question of survival isn't just academic. It's the key to understanding how matter moves between stars. How much erosion can an interstellar object endure before it's obliterated? The answer, surprisingly, is a lot. Laboratory experiments and computer models suggest that cosmic rays can only penetrate a few centimeters into solid rock or ice. That means most of an object's interior remains untouched, even after millions of years. The outer crust might lose mass through sputtering, atoms literally knocked off by radiation, but the bulk stays intact. In other words, space erosion gives these objects a weathered exterior, but leaves their inner composition largely pristine. That's why finding and studying them is so exciting. They're like time capsules, with the surface acting as a cosmic diary of radiation exposure, and the core preserving the original chemistry of their home systems. This is also crucial for planning future interstellar probes. If a naturally ejected rock like 3IATLAS can survive for tens of millions of years, it means that human-built probes, properly shielded, could too. Radiation may degrade electronics and strip surface coatings, but bulk materials, especially dense metals and composites, can withstand galactic exposure longer than we once thought. Engineers studying interstellar probe designs, like those proposed for the Interstellar Probe Mission or Breakthrough Starshot, use these natural examples as test cases. How does interstellar dust erode surfaces at high velocity? How much radiation shielding would a probe need to survive thousands of years? How do cosmic rays affect molecular structures and onboard sensors? ʻOumuamua can't answer these directly, but it provides the baseline data, the empirical proof that long-term survival is possible. Perhaps the most fascinating lesson from 3IATLAS lies in molecular endurance. While radiation constantly bombards it, some complex organic molecules can still survive or even form on its surface. That's because deep space chemistry thrives on extremes. When high-energy particles hit ice, they can trigger reactions that create amino acids, alcohols, and other prebiotic compounds. This phenomenon has been demonstrated in lab experiments simulating cosmic ray exposure. That means 3IATLAS isn't just a rock, it's a chemical laboratory that's been running continuously for millions of years. It may have built up layers of organic residue over time, each one a molecular history of its journey. And while it's unlikely that life itself could endure such an environment, the building blocks of life certainly can. This realization has huge implications for panspermia, the hypothesis that life's ingredients can spread between star systems on natural carriers like comets and asteroids. If 3IATLAS can keep organic molecules intact through such long, harsh conditions, then interstellar chemistry is not just possible, it's thriving. Studying 3IATLAS gives us a head start in preparing for our own galactic journeys. By analyzing how radiation reshapes materials, we can design spacecraft with better shielding and predict how long onboard systems can last. By understanding erosion rates, we can estimate how much dust or plasma shielding will be required for ultra-fast missions. Even more intriguingly, this rock's resilience hints that physical communication across the stars is feasible. If chunks of matter can survive intact across light years, so can our future probes, or even messages encoded in matter, like physical archives of human knowledge launched into the void. In essence, 3IATLAS is proof of concept. Nature has already done what humanity dreams of doing. It sent something across the stars and kept it intact. So next time you're frustrated that your phone battery dies before dinner, remember 3IATLAS, a rock that's been on low power mode for 50 million years and still works perfectly fine. If it can survive supernova shockwaves, cosmic rays, and billions of kilometers of emptiness, maybe there's hope for human technology yet. But jokes aside, this humble traveler offers something profound. It teaches us that the galaxy is not a barrier. It's a medium. Objects, molecules, and even information can move across it, endure within it, and emerge from it transformed but unbroken. 3IATLAS isn't just a visitor, it's a veteran, a survivor of radiation, silence, and time itself. And in its endurance it carries a message for every future probe and every curious civilization daring to cross the stars. The journey may be long, the void may be harsh, but persistence is the universe's oldest technology. For as long as humanity has gazed up at the night sky, we've been curious about what lies beyond our sun's domain. But until recently, that curiosity was purely theoretical. We studied the stars, the planets, and the faint glow of distant galaxies. But nothing from out there had ever come here. Then, in the span of a few short years, 3 visitors changed everything. ʻOumuamua, Borisov, and 3IATLAS. They weren't just objects to observe. They were physical proof that the solar system isn't a sealed bubble. They came from elsewhere, crossing the invisible boundaries that once defined our cosmic backyard. And once humanity realized that interstellar objects actually exist, and that we can detect them, one question became irresistible. Can we chase one? Spoiler, not easily. When 3IATLAS entered the solar system, astronomers did what scientists always do. They pointed every telescope they had at it. But by the time we discovered it, it was already speeding past at tens of kilometers per second. Long gone before we could even design a mission concept. It was like spotting a shooting star, realizing it's actually an alien messenger, and then watching helplessly as it vanishes into the void. Cue NASA's collective sigh. We can't catch it, but we can definitely stare at it really hard. The biggest obstacle in studying or intercepting interstellar visitors is simple. We always find them too late. Objects like 3IATLAS are incredibly faint until they're already inside the solar system, reflecting just enough sunlight for our telescopes to notice. By then, they're already moving away at insane speeds, often faster than any spacecraft we've ever built. To truly study one up close, we'd need to detect it early, while it's still inbound from the outer solar system. That means spotting an object just a few hundred meters wide from billions of kilometers away, a task roughly equivalent to finding a firefly in a hurricane using binoculars. but it's not impossible. New telescope systems like the upcoming Vera C. Rubin Observatory in Chile will revolutionize how we scan the sky. Its 8.4-meter mirror and ultra-wide field camera will take a full snapshot of the visible sky every few nights, automatically identifying transient objects. When it goes fully operational, it could give us months, maybe even a year, of warning before an interstellar object's closest approach. And that advance notice could change everything. With enough lead time, humanity could launch an intercept mission, a spacecraft designed to rendezvous with a fast-moving interstellar traveler. It sounds ambitious, but several mission concepts are already on the drawing board. NASA scientists and engineers have proposed several ways to chase down future visitors. One of the most promising is the Comet Interceptor mission, led by the European Space Agency, ESA. Although it's not specifically designed for interstellar targets, it's built to sit in standby mode at the L2 point, about 1.5 million kilometers from Earth, waiting for an interesting comet or interstellar object to be discovered. Once identified, the probe could launch from its position and intercept the object on the fly, capturing close-up images and analyzing its composition before it disappears. Then there's the more ambitious interstellar probe concept, a mission that aims not to chase a visitor, but to become one. The idea is to build a spacecraft capable of leaving the solar system entirely, traveling beyond the heliosphere, the bubble carved by the sun's magnetic field, and into the raw interstellar medium. This probe would measure the environment between stars, collecting data that no human-made object has ever gathered. Proposals for such a mission include using solar sails or nuclear electric propulsion to reach speeds of 1520 AU per year, astronomical units, or roughly 3-4 times faster than Voyager 1. Even at that pace, it would take decades to leave the heliosphere, but the reward would be unparalleled. Direct exploration of the same environment 3IATLAS traversed for millions of years. In essence, we're trying to build a robot version of 3IATLAS, a durable, unrelenting traveler that can survive the cold, radiation-filled expanse of interstellar space. The technological challenges of chasing or following interstellar objects border on absurd. For one, speed. 3IATLAS was moving at around 26 kilometers per second relative to the Sun, far faster than anything we've ever launched. The Parker Solar Probe, humanity's current speed record holder, reaches about 190 km at perihelion, but it does so by diving perilously close to the Sun. Getting a probe up to that speed and directing it toward an unpredictable interstellar object is like trying to throw a paper airplane into a tornado and hit a specific leaf. Then there's the navigation problem. Even if we detect an interstellar object early, its trajectory changes as it interacts with solar radiation and outgassing effects, if it has volatile ices. That means our spacecraft would need autonomous navigation, real-time AI adjustments, and possibly laser communication to keep up with new data. We're talking about a mission that would need to think for itself while hurtling through space at tens of kilometers per second. And, of course, there's the issue of distance and communication. Once a probe goes beyond a few astronomical units, signals take hours to reach Earth. A true interstellar mission would operate in radio silence for long stretches, a lonely wanderer guided by pre-programmed instinct and physics alone. Still, Humanity has a knack for doing impossible things. We've landed on comets, flown helicopters on Mars, and sent twin probes beyond the edge of the solar system. The idea of chasing an interstellar object no longer feels like science fiction, just science with an attitude problem. Beyond the engineering thrill, there's a profound reason we care about these cosmic visitors. Interstellar objects like 3IATLAS are the only natural materials from other star systems we can study directly. They're messengers from alien worlds, carrying the chemistry of distant suns and the physics of formation processes light years away. By intercepting one, we could literally sample another planetary system without leaving our own. It would be our first tangible link to the galaxy beyond, a handshake across the stars. And perhaps more importantly, these missions feed something deeply human, the need to reach outward. Every time we detect a visitor like 3IATLAS, we're reminded that space is not a closed neighborhood. Matter moves between stars. Systems exchange fragments. The universe is more connected than we once imagined. So yes, maybe NASA can't catch interstellar objects yet. But as they like to say, can't in space exploration really just means give us 30 years. The next time an alien rock hurtles toward the sun, we might be ready. Engines primed, trajectory locked, humanity's collective gaze fixed on the horizon. And when that day comes, it won't just be another mission. It'll be a statement that we're no longer content to watch visitors pass by. We're ready to follow them home. When you think of farewells, you might imagine a slow fade, a sunset, a wave, maybe even a sentimental soundtrack. But the universe doesn't do sentiment. When 3IATLAS left the solar system, it didn't linger, it didn't look back, and it definitely didn't sign the guest book. It just accelerated outward. Sunlight glinting faintly off its surface one last time before it vanished into the dark. In cosmic terms, it was the ultimate Irish exit, the kind where the party's still going, but the guest of honor has already hit hyperspace. For astronomers, watching it go was both exhilarating and bittersweet. Here was a genuine alien object, not a product of imagination or science fiction, but a solid, physical emissary from another star. And just as quickly as we found it, it was gone. Its outbound path, measured in careful arcs of light and gravitational models, told the whole story. 3IATLAS was unbound. The sun's pull, mighty enough to control entire planets, couldn't hold it. Once it rounded perihelion, its closest pass to the sun, it began accelerating outward again, headed back into interstellar space and never to return. As it departed, telescopes across the globe tracked it until they couldn't. The object grew fainter each night, slipping from magnitude 18 to 19, then 20, beyond the limits of even the largest observatories. One by one, the instruments gave up, like eyes straining to see a fading ember in an ocean of darkness. And with that, 3IATLAS was gone. Its story left to the data stored in servers and the memory of those who caught its fleeting visit. From a purely orbital perspective, 3IATLAS's exit was predictable but humbling. Its trajectory formed a hyperbola, open-ended, eternal, the mathematical signature of freedom. The energy of its motion, known as specific orbital energy, was positive, meaning it had more kinetic energy than the sun's gravity could ever reclaim. It would continue to drift outward indefinitely, slowing only imperceptibly as the light of our star faded behind it. Calculations show that within a few thousand years, 3IATLAS will be far beyond the influence of any planet, and in about 1,000,000 years, it'll be a distant speck among the interstellar dust, indistinguishable from the background of stars. Its velocity relative to the Sun, about 26 kilometers per second, ensures that nothing in our system will ever bring it back. It's like tossing a pebble into the air so fast that not even Earth's gravity can pull it down again. But what's extraordinary is how rare these encounters are. Though astronomers estimate that trillions of interstellar fragments wander the galaxy, space is unimaginably vast. Our solar system is a microscopic target in that expanse. Catching one in the act of passing through is like spotting a single dandelion seed drifting across a continent. The fact that we've seen 3 in just a few years, ʻOumuamua in 2017, Borisov in 2019, and 3IATLAS in 2024, might say less about their frequency and more about our improving ability to notice them. Our eyes on the sky have grown sharper, and the universe hasn't changed. We just finally learned to pay attention. There's something deeply philosophical about watching a visitor like 3IATLAS leave. It's a cosmic version of closure, an acknowledgement of how transient our glimpses into the wider universe truly are. Each interstellar object is a messenger from beyond, but it never stays long enough for conversation. We get a few weeks, maybe months, to collect data, argue about its composition, and speculate wildly. Then, poof, it's gone, leaving behind only math, pixels, and wonder. Yet, in those brief encounters, the universe offers us a mirror. When we trace 3IATLAS's outbound path, we're reminded that everything in motion eventually leaves something behind. Stars shed planets, galaxies fling stars, and even we, tiny descendants of stardust, will one day send pieces of our own world drifting into the void. Humanity's spacecraft, from Voyager to Pioneer, are already on their own slow exits, future fossils of civilization heading for interstellar night. 3IATLAS may be alien, but its journey isn't unfamiliar. It's the same path our creations will take, just reversed. It's poetic to imagine that someday, far away, an alien civilization might detect one of our outbound relics, perhaps a probe, or even a grain of dust from our solar system, and wonder where it came from, what forces ejected it, and what strange beings once lived under the light of that pale yellow star. The act of watching 3IATLAS leave is, in a way, watching our own future in miniature. Unlike comets that leave behind glowing tails and photogenic arcs, 3IATLAS's departure was silent and almost invisible. No dramatic outburst, no blaze of evaporation. It didn't even gift us a final flare of reflected sunlight. In the end, it simply drifted out of range, crossing the orbit of Saturn, then Neptune, then into the realm of the Kuiper Belt, where frozen debris marks the solar system's edge. Beyond that lies the Oort cloud, a theoretical sphere of comets so distant that sunlight takes months to reach them. When 3IATLAS crosses that final frontier, it will pass through the threshold that separates the sun's influence from the true interstellar medium. That invisible boundary, known as the heliopause, marks the outermost breath of the solar wind. Once it's beyond that, 3IATLAS will be free of our star forever, a traveler among the galactic tides. There's something humbling about that. The idea that this small, unassuming object will outlive our sun, continuing its journey long after our own civilization has turned to myth. Of course, scientists, being human, met this cosmic farewell with equal parts awe and dry wit. One astronomer described it best. It came, it spun, it photobombed our telescopes, and then it Irish exited the galaxy. Another added, "We didn't even get a selfie." That humor is more than levity. It's coping. It's our way of acknowledging how fleeting and fragile discovery can be. In the vast scale of the cosmos, we are the lucky observers who happen to be looking up at the right moment. Though 3IATLAS itself has vanished, it leaves behind a legacy that will ripple through astronomy for decades. The data it provided, its light curve, its color profile, its orbital parameters, will refine our models of interstellar population dynamics. It helped prove that such visitors aren't once-in-an-eternity anomalies, but part of a continuous galactic exchange. Each detection improves our understanding of how planetary systems eject material and how that material weaves the galaxy together. It also gave us something intangible yet profound: perspective. For centuries, we imagined the solar system as a closed set, a family of planets orbiting in isolation. Now, we know it's a node in a sprawling web of exchange. 3IATLAS reminded us that borders in space are imaginary. The Milky Way doesn't recognize here and there. It's all part of one vast circulation, one unbroken story of motion. And so 3IATLAS leaves the stage. No applause, no encore, just a steady fade into the darkness it came from. But in that quiet exit, it leaves behind the echo of its passing, a reminder that even the briefest visit can change how we see the universe. After all, it's not every day that a rock from another star swings by just to say hello and goodbye before disappearing into eternity. When 3IATLAS vanished into the dark, it didn't disappear into nothing. It simply returned to the great archive of the cosmos. Because if there's one thing the universe does better than expand, it's remember. Every photon that leaves a star, every atom that drifts between systems, every interstellar wanderer like 3IATLAS, all of it carries information, a trace of where it's been and what it's endured. The universe, vast and silent as it seems, is one immense memory, written not in words but in starlight, motion, and matter. 3. Atlas is now part of that record, a wandering page in the galactic library, etched with the story of its birthplace. A star system long forgotten, its worlds now perhaps gone or changed beyond recognition. And yet, even across tens of light years and millions of years of travel, it still bears those ancient fingerprints. The isotopes forged in its parent star, the dust of its native nebula, the chemical scars of its ejection. It carries those clues the way fossils carry traces of ancient seas, silent, immutable, waiting for someone to read them. That's the strange, beautiful truth about interstellar visitors. They are messengers from memory itself. Each one is a timeline fragment, drifting across the Milky Way, reminding us that nothing truly stands still. Everything in the universe, stars, comets, people, is part of a grand exchange, a circulation of matter and meaning that has been ongoing since time began. When we say the universe remembers, we don't mean it in a mystical sense. It's literal physics. Every motion, every collision, every burst of light alters the cosmic ledger in some way. The faint microwave background still carries the imprint of the Big Bang. The elements in our bones still carry the ratios forged in long-dead stars. The orbit of every planet encodes the gravitational past of its system. Even the emptiest region of space hums faintly with the accumulated energy of all that has ever happened. The galaxy, then, is not a collection of isolated systems, but a memory network. 3IATLAS is just one of countless couriers moving between nodes, sharing the chemical and kinetic gossip of the stars. Its trajectory is a physical connection between two stellar histories, where it came from and where it passed through. Someday, perhaps millions of years from now, it may enter another system, brushing past alien planets and leaving faint dust trails that some distant astronomer might one day detect. And maybe, just maybe, they'll wonder about its origin. They'll point telescopes, measure its speed, study its spectrum, and ask the same questions we did. Where did it come from? How long has it traveled? Who first called this rock home? If the universe is a library, then 3IATLAS is a wandering book, one of infinite volumes, each containing a fragment of some cosmic autobiography. What makes 3IATLAS extraordinary isn't just that it crossed our path, but that it endured long enough to do so. That endurance makes it a literal time capsule, a survivor from another era of the galaxy. When it formed, the Milky Way itself was younger. Stars that have since gone supernova still burned brightly. The spiral arms were arranged differently. Its journey has outlasted civilizations, planets, and even some suns. And yet, through all of that, it kept moving. That's the thing about motion in the universe. It's eternal. There's no stopping in space, only changing direction. Planets orbit, galaxies spin, stars drift, and even the smallest dust grain traces a trajectory that will continue until the laws of physics themselves retire. In that sense, motion is memory. Every orbit is a record of a past encounter, every drift a signature of origin. 3IATLAS's motion now records its brief dance with our sun, a small gravitational nudge added to its endless story. Its velocity vector carries that mark forever. Long after we're gone, that motion will persist, whispering across light years that once it passed through a system with 8 planets, one of which looked up and noticed. It's funny, in a cosmic sense, that humans, so ephemeral, so temporary, are obsessed with remembrance. We build monuments, write books, and send golden records on spacecraft in the hope that someone, somewhere, will know we existed. Meanwhile, the universe quietly archives everything for us. Every photon that leaves Earth carries a bit of our story. Somewhere, thousands of light years away, our radio waves are still expanding outward, faint echoes of our civilization etched into the background hiss of space. So maybe, just maybe, 3IATLAS isn't the only messenger in this exchange. We're sending our own emissaries out there too. Spacecraft like Voyager, New Horizons, and Pioneer, each carrying data, music, and greetings into the void. Someday, far in the future, another civilization might detect one of them and ask, "Who threw this Earth stuff at us?" And they'd be right to wonder, because by then Earth itself might be long gone, yet that tiny piece of metal, like 3IATLAS, will still be drifting, still remembering. When you step back and look at the galaxy not as an empty void but as a living system of exchange, the boundaries between stars begin to dissolve. 3IATLAS's story isn't just about a visitor leaving another system, it's about connection. It's evidence that matter doesn't stay loyal to one star forever. It travels, it transforms, it shares its history. If you zoom out far enough, every interstellar object is part of one enormous galactic bloodstream. A slow, eternal migration of dust and rock and starlight. Some bits end up in comets, some collapse into new planets. Some, like 3IATLAS, drift between systems indefinitely, carrying whispers of one world into another. The Milky Way remembers through them, a living record written not on parchment or stone, but in orbits and trajectories. That's the beauty of cosmic memory. It doesn't fade, it just moves on. As 3IATLAS continues its lonely journey through interstellar space, it remains a silent historian, carrying within it the chemistry of its birth and the imprint of every encounter since. It may never be seen again, but that doesn't mean it's forgotten. Its motion, its atoms, even its faint gravitational influence on other bodies, all of it remains recorded in the unfolding symphony of the cosmos. In the end, perhaps that's the universe's quiet promise. Nothing truly disappears, only transforms. Every atom that leaves one world eventually finds another. Every photon that escapes a star illuminates something new. And every interstellar traveler, whether it's a rock from another star or a probe from our own, becomes part of the eternal memory of starlight. So, as 3IATLAS sails deeper into the dark, carrying the history of a distant sun, we can look up and know this much. We too are written into the same cosmic story. Our atoms, our light, and our curiosity are part of that universal memory, drifting, shining, and remembering. Because the universe never forgets. It simply keeps moving.